Hello, Professor Cross. Can you hear me?
Sorry, I was still muted. Yeah, hello. Nice to meet you.
Nice to meet you. Uh, I think you can share your slides. Maybe you can have a simple test.
Yeah, let me do it. Oh, it's saying that someone else is sharing, so I replaced that, yeah.
Okay.
So I hope
Okay. Now,
should be in presenter mode now. Can you see that in presenter mode? I'm just flicking through the slides. Can you see that?
oh yeah,
Good.
Yeah, I can see that.
Brilliant.
you know what's well.
Cool.
Oh
Okay.
yeah. Professor Cross, we invite Professor Liu as the host for your talk.
Thank you very much and very nice to meet you.
Professor Liu, maybe to un-
Oh, sorry, I think the connection was bad there. I didn't understand what you said.
Oh yeah, there is something wrong with my internet.
Yeah, there is something wrong with your internet. We didn't hear you.
It seems better now because your camera is frozen as well, but now it's not. So maybe it sorted itself.
徐老师可以，应该可以了，看着你是流畅的了。
Okay, okay. 刘老师，我们大概一会儿提前2到3分钟的时候会，就是共享一下我们的那个视频，咱们EEH那个视频，视频播放结束之后，呃，
徐老师，你有点卡。你说你要播放，提前2到3分钟播放你的视频，是不是？
对 EEH 的那个宣传视频，
嗯，好。航宣上视频是3分钟还是5分钟？
好像2分多不到3分钟。
哦，好。那我就是你们播放视频完了以后，我再介绍。
哎，对，你就可以直接就开始准备你的那个介绍就可以了。
好。
Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present and future is the mission of Eco-Environment and Health. Eco-Environment and Health is a journal initiated by prestigious scientists with a strong editorial board including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design and broadcasting. The experts will accompany you like a harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
We will start. Good morning. Good afternoon, everyone. Good morning, Professor Stephen Cross. Welcome to the 102nd session of Talk at EEH. I'm Liu Yang from Kunming University of Science and Technology. You can call me Yang. And also, I am the early career board member of Eco-Environment&Health. Let me briefly introduce the EEH journal to you. Eco-Environment&Health is a multidisciplinary peer-reviewed journal focused on the concept of One Health to promote green and sustainable development, dealing with the interactions among ecology, environment, and health, and the underlying mechanisms and interventions. EEH covers a variety of research areas, including but not limited to ecology and biodiversity conservation, environmental behaviors and bioprocesses of emerging contaminants, human exposure and health effects, and evaluation, management, and regulation of environmental risks. The journal has been indexed by 14 international databases, including ESCI, Scopus, PMC, CSCD, and DOAJ. In 2024, EEH achieved its first impact factor of 70.6, ranking the 8th out of 374 journals globally in the field of environmental science. Building on this momentum, we remain committed to advancing rigorous, impactful research. Talk at EEH was founded in May 2022, serving as a platform for scientists to share thoughts on ecology, environment, and health. So far, it has invited over 100 scholars from home and abroad to share their research results and academic viewpoints. Today, we are honored to invite Professor Stephen Cross from the University of Birmingham, UK, to deliver a lecture. Professor Cross is a leading eco-hydrologist whose work examines the fate and transport of contaminants and eco-hydrological interfaces and their implications for environmental and public health. His strongly interdisciplinary research investigates the impacts of global environmental change on hydrological fluxes, biogeochemical cycling, and eco-hydrological feedback functions in complex landscapes. His group focuses on multi-component reactive transport, combining the interactions between emerging and legacy pollutants, and how these are influenced by changes in land use and climate. Today, we will speak on One Health risks of micro and nanoplastics, linking transport mechanisms to exposure risks and outcomes. So, Professor Pearls, an explanation, because you see that there are few people in the Zoom meeting room. That's because it is not very convenient for Chinese audience. So my colleague Xu Ming will help us to broadcast our lecture on Bilibili platform. The messages and questions from various platforms will be transferred to the chat dialogue box in the Zoom meeting room. Okay, I hope that helps. Next, let's welcome Professor Cross to give the lecture. Professor Cross, please share your slides. Thank you.
Thank you very much for having me and for this very kind introduction. I hope you can see the slides okay in full presentation mode now. Yeah, I'm going to talk about the health risks of micro nanoplastics and how we, as environmental scientists, I'm a hydrologist by training, can improve the understanding and contribute to the understanding of what constitutes exposure risks to micro nanoplastics. I start usually because I'm getting asked quite a lot after our group has worked a lot on the fate and transport of different types of emerging contaminants and legacy contaminants, from nutrients to chlorinated solvents to pharmaceuticals at interfaces between groundwater and surface water. Over the last 8 to 10 years, a lot of our research has started to focus on micro nanoplastic, its sources, fate and transport, and uptake in the environment. And I get often asked, why are you focusing on plastics? And my slightly joking answer to that is because we actually carry some responsibility working here in Birmingham, because as being the cradle of industrialization in the 1800s, Birmingham was one of the places where plastics was invented. I nicked this slide from some of my polymer chemist colleagues, who are very proud that Alexander Parks was a chemist working in Birmingham, was one of the first who invented synthetic polymer. At that time, you still named things, inventions after yourself, so it was called Parkesin. This was really one of the first industrially used synthetic polymers. You see some of its applications from doorknobs to light switches, etc., on the right-hand side. And I remember still that very opaque type of plastic in the household of my grandmother, for instance. So it was a type of plastic that was around for quite a while. We often refer to these types of plastic as the first type of plastics. It was an incidental finding. It was something that was, I don't know what he tried to do when he mixed a flammable nitric ester with cotton cellulose, so something that could have ended up with a big bang. But it was an incidental finding to actually create this synthetic polymer, like so often in science. But at that time, plastic was seen as a solution to many of the environmental problems, because it replaced many natural materials like ivory and others that were rare materials that had their use had a significant impact on environmental functions, well-being, biodiversity, and so on. So initially, the story of plastic was a very positive one, as shown also here in that slide, where you can see how, if you just look at the front cover of the Life magazine 70 years ago, there was a hype, a real welcoming of plastic as a cheap material, as an supposedly environmentally friendly material that was easy to manufacture, lightweight, easy to transport, and made life very much easier. And I won't go too much into detail today how much our life depends on plastic, but our economies globally are very intensively coupled to the use of plastic. I come back to that just at the end when I talk about regulations. Nowadays, the perception of plastic has shifted quite a bit. As you can see on the right-hand side, it's now an almost 10-year-old front cover of National Geographic, where you see that a lot of focus on plastic these days is on the problem of the end that plastic creates at the end of its life, of its use, when it becomes plastic waste. We've been talking a lot previously and work still a lot also on the impact that plastic and plastic waste is having on the environment, in particular microplastic. And the attention to this really in the public was raised by some fantastic advocates to the problem, like Sir David Attenborough and his Blue Planet program that was really changing the way how plastic waste is perceived and how it is perceived as a problem, a global problem that affects us all. That's something that we as scientists have been saying for a while, but you need this outreach as public advocates of a problem as well, like he and many others have been since to raise awareness of this problem. So there has been an awareness of the environmental risks associated with the waste that and the uncontrolled waste production from plastics, in particular micro and nanoplastics. So there's really tiny particles that, as microplastics, a majority is not visible. Nanoplastic, none of that is visible by the pure eye. So we talk about microplastics being particles smaller than 5 or 1 millimeter, nanoplastics being smaller than 1 micrometer usually. We get, however, more and more aware that there are not only environmental consequences, but that there are direct human health consequences from exposure to micro and in particular nanoplastic. The evidence is still patchy, it's quite fragmented, but it is rapidly growing. It of course is very difficult to provide mechanistic evidence of what the impacts of micro nanoplastic exposure on human health are, because we don't have a control group. We know there's no part of the population that is not affected by micro nanoplastic exposure. We work a lot in the Arctic. I had a postdoc just coming back from work in Antarctica. He's going back to the high Arctic, Svalbard, very soon. And we find atmospheric fallout of micro nanoplastic there everywhere. So you can't escape that exposure. So we can't compare impacts of people that are more exposed to people that are not exposed at all. However, there have been findings that microplastics are in particular able to enhance the global burden of non-communicable diseases. So those non-infectious diseases, in particular, through uptake into our gastrointestinal system, as well as respiratory tract. But we've also seen increasing evidence of micro nanoplastic that have become fully circulated in human organisms. Very often these are still detections of micro nanoplastic particles or some of their additives that we are very concerned about as well in different organ systems of humans. A lot of the research on the mechanisms these are causing, on the disease mechanisms, is then done in cell and organ cultures, of course, not in humans directly. But what we are seeing, and there's increasing evidence for that, is that exposure to many micro nanoplastics and the additives can enhance inflammatory conditions. It can interfere with the hormone system. So there's a lot of additives used in plastics that are endocrine disrupting substances, like many of the phthalates or bisphenols in there. Bisphenol A, BPA, quite often just abbreviated, is one that we know very long about because it not only originates from plastic, but also many other products. And you see quite often on plastic bottles, in particular those used for babies and infants, that they carry this BPA-free sticker because we regulated industries really have made big efforts to reduce the use of some of the bisphenols, sometimes unfortunately only replacing them with other bisphenols that are not better, sometimes even worse. If you look into where many of these different polymers have been found, and this is shown from a paper where we tried to summarize the state of knowledge 2 years ago. It was published last year, but it summarizes the state of knowledge up to the beginning of 2024. You see that if we look into some of body fluids, for instance, most of the polymers have been detected there now. Very often it's the additives that we are at least as concerned about as the polymers. That are the backbone of the plastics. But the real challenge here is that it's a complexity of plastic as a product, because it can consist of many different types of polymers. They all carry different ecotoxicological and toxicological risk profiles, but they also come with different cocktails of associated chemicals like additives, so that we have tens of thousands of different types of plastics. And I try to explain to people very often when they ask, like, why is the knowledge so fragmented? And why do we find that sometimes plastics cause an impact, but other types of plastics not? And I tell them, look how long it took to establish the health impacts of smoking, where you had a clear the chance to compare an exposed group to a clear control group, and where you had to deal with much less complex contamination than when we talk about plastics. This took decades. Plastics is such a more complex group containing contaminants as well, so that we will of course find some that we have to be worried about less, luckily, but we have to find those conditions that we should worry more. In order to assess the risks, however, it's not only important to see what ends up in humans, but to be able to explain why does it end up there, and how is that related to human exposure. Human exposure is very complex. It varies between individuals based on their residence in different indoor and outdoor environments. There's a lot of emission of microparticles. We call them secondary microplastics if they're not designed to be microplastics, from furniture, from clothing, textiles, and so on. But of course, also in outdoor environments, from road markings, building materials, the absolutely critically understudied class of tire and road wear particles, which can constitute potentially up to 50% of all the micro nano plastic. I mean, it's more synthetic rubber particles that we are exposed to. And we all are differently exposed to them based on where we live, our behavior, our occupational backgrounds, what type of environment we work in. I'm a keen runner. For me, it depends certainly on what types of the day I'm running, whether I run in an inner city area or somewhere outside the city I live in. So all of this has a significant impact on our exposure, and we need to start understanding what controls that exposure if we want to assess the risks. As a hydrologist, the contribution we from our group make to that is to try to understand how do rivers and in general water connect sources of plastics. I'm not going to talk about the sources that much today, but the connection of wet sources, activation of wet sources, and the connectivity that is established through hydrological processes, and how different types of ecosystems or us humans are actually exposed to those plastics based on the fluxes of water and activation of those sources. And you might think, we should know that relatively well. There's been a lot of work on that, in particular, looking to the global oceans. I think we know very little about that. And I give some evidence here. I don't want to discredit that work that I'm showing here. I think we need some starting points, and these are really great starting points. But I think they also evidence how little we actually know. What you see on the left-hand side is a prediction of global distribution of mismanaged plastic waste. These are not only micro nanoplastic, this is mismanaged plastic waste independent of its particle size. So macroplastic is included there. I will show you some models. This is not a model from us. This is an output from the ocean cleanup. And the study actually using that is shown underneath. I want to just highlight there are models predicting that based on the production of mismanaged plastic waste in different countries per capita and assumptions how that waste is moving. You may have come across a lot of media attention that was paid to some studies a few years ago that was showing, and you see that on the right, how much plastic is emitted by what type of rivers to the oceans. I want to stress here already one thing I will really highlight today is oceans are by far the major sink of plastic. There's no terminal sink of plastic. Really, at least the oceans are not. And we have many other long-term sinks of plastic on the way to oceans, but hardly any plastic that we have emitted has yet reached the oceans. But what these studies have shown, and they are all modeling studies, there was a bit of a dispute. Is it 10 or 100 rivers, sorry, 10 or 20 rivers globally that are contributing 80 to 90% of plastic to the oceans, and which of these largest rivers in the world these are. There are a few studies debating that a few years ago. Some of the authors have 2 years ago joined up, and they actually came up, you see that on the in the blue line here, saying like, actually it's not 10 or 20, it's more likely 1,000 rivers that contribute 70%, not 80 or 90% of plastics that we find in the oceans. This is a 2 order of magnitude change to what we still thought a few years ago. And again, I don't want to discredit any of that work, but I think it highlights fantastically that that we are still in the middle of a learning process, right? We are just starting to understand what controls the fate and transport, and with that also the exposure to and impact of micro nanoplastic. We are running a global model as well, in contrast to other models that are out there. We use the same sources, and they are not coming without uncertainty. So the sources usually are assumptions about mismanaged plastic waste globally for the year 2010. This is a World Bank data set. We are 15 years later now. Even 2010, some of that was not the most current anymore. What we do differently is that we distribute these particles or parcels of mismanaged plastic waste in subcatchments, and then really route how likely it is that, I hope you can see my cursor, how likely it is that they reach a connector, a surface water feature that then routes it or gets it into a stream network, and we route it through this stream network then based on very basic sedimentary transport knowledge, where we don't have to reinvent the wheel. That's a lot of mechanistic knowledge, physical knowledge that has been out there and used in other sediment transport models for a long time already. We come up with a slightly different picture. And I have to stress, these are representations for 2010. A lot has changed, of course, since then, right? A lot of waste management has changed, in particular across many Asian countries, many Latin American countries, unfortunately not that much in many European countries. There were really good standards in many European countries, and others, including the one I'm in, we are very slow. Wales is a great part of Britain, where a lot of recycling and waste management is fantastic. Many of the English cities are very poor in that still, compared to many other European countries. If you look, however, in our prediction, we predict much more mismanaged plastic waste being accumulated in Central Europe, in Western Asia, but also in central parts of Asia. And that's one of the things that previous models have neglected. They've mainly focused on countries that are discharging plastics to the ocean based on having a coastline, but they excluded countries that don't have a coastline. That meant if you lived in Switzerland or somewhere in Central Asia, your plastic, according to that models, would have not reached the oceans, which of course is not true, because the rivers are big connectors, right? And if you live in Switzerland, the Rhine, for instance, or the Rhone, I will show you some results from the Rhone, will transport your plastic further downstream. But we find that a lot of mismanaged plastic waste, if you look on that figures down here, is actually sitting in areas that are in really far distance from the coastlines. I work a lot, not only in China, but also in India and the Gangetic Plains. We see a lot of mismanaged plastic waste. The majority of that is not close to the coastlines. So a lot of previous models have focused in particular on emissions from 50 kilometers away from the coastlines and up to 200 kilometers away from there. And we have shown that a majority of plastic sits even further away from the oceans. One thing we have also shown is that a lot of plastic, you see that on the lower left here, is emitted into river networks that are endorheic. That means that are rivers that never see the ocean, either naturally because they never did, or because of over obstructions, like we see in particular at the Colorado River in the southwest of the US. This is model work, right? If you don't validate that as much as it's possible, it, in my view at least, is relatively useless, because unvalidated models, non-falsified models, you can tell people everything with it. So let's compare it to some observations. These are some observations from the Okavango Delta, one of the world's largest endorheic basins. So it's in the southern part of Africa. You see the map here. Has a huge panhandle, where basically in this endorheic basin flux seizes of water and infiltrates. And we had the luck during COVID times to get our hands on several cores from collaborators that were looking into micro nanoplastic accumulation in that panhandle, quantified how much micro nanoplastic also microplastic only, sorry, not nanoplastic. Also, what type of polymers and what type of particles we find there. We saw there's quite a bit of variability. Don't focus that much on that. And this comes with a lot of uncertainty. We have less than a dozen cores actually to look into here. But one thing we find is significant amounts of microplastic. If we add that up and we know how much sediment is deposited in that areas, then we see that based on how small particles we are analyzing, whether we analyze down to 20 micrometers, which often is the standard, or down to 64 micrometers, which many other studies have been using, we find either 10 to 75 or 200 to more than 300 billion particles. The world's ocean are supposedly containing 5 to 50 trillion plastic particles. So we are in this one endorheic river already seeing per year the accumulation of a large fraction of what actually so far is supposed to have reached the oceans. Highlighting here again significant uncertainties. The mass balances of these are not really matching. Also, if we look into what rivers globally, jumping back into our model, are having the potential to carry most micro nanoplastics, the majority of micro nanoplastic actually is accumulated in river basins that are smaller than 1,000 square kilometers, independent of where they are. Yeah, their drainage area usually is smaller. The largest rivers, that's absolutely correct. They can accumulate a lot of plastic, but we don't have that many of them. And there are many other issues. I come back to that in a second. Again, looking into zooming in a little bit into that model here into the Ganga River, where we work a lot, and I work a lot in Vietnam as well, in particular northern Vietnam, but we here took the example of the Mekong River. We see, if we quantify how much of the mismanaged plastic waste that has reached that river basins since the 1950s, when industrial use of synthetic polymers really kick-started, we see that less than 3% of all that mismanaged plastic waste that has ever entered that river networks has exited to the oceans. The important learning point from that is a lot of that plastic stays in that river systems. That means we, on the one hand side, it's much closer to us, to our food production systems, for instance, but also we have created a legacy. We talk about micro nanoplastic as emerging contaminants, but we created a legacy here already, given how long living they are as materials as well, a legacy for future generations. There are multiple reasons for that, and I'm not going into too much detail with this mechanistic studies, but I gave you the references of a couple of key papers here. One reason for that is that rivers interact a lot with their stream beds, with the river beds and with the river banks. And in contrast to what happens in the oceans, where it's mainly gravity settling of particles, we find a lot of forcing of micro nanoplastics with advective flow of surface water into streambed sediments and river banks. We call that hyporheic exchange. We have done research on that in our group for a long time, also for many solutes. The consequence of this advective forcing of particles into the streambed is that they go deeper into the streambed. That means they are not remobilized as quickly as particles that have settled just by gravity. But they also explain why in a lot of the research that we are doing that's more experimental and field-based, we find a lot of low-density plastics that we would think would be floating in rivers, but we actually find them in streambed sediments. We couldn't explain that by gravity settling. We can only explain that by this advective forcing of particles with a flow, as it's shown here, into the subsurface. And due to that, the transport of micro nanoplastic in river networks, it's estimated here with a very different type of model that I'm happy to go into detail if there are questions. But we estimated that it takes on average 7 years to transport particles through this sedimentary part of a river. And there's a lot of the mass of micro nanoplastics sitting in that sediments. And we are talking about One Health a lot today. This affects not only micro nanoplastic. We do a lot of research where we're showing that this affects many other particles as well, whether it's viruses, bacteria, or things like antimicrobial resistance attached to particles that can be trapped in the sediments downstream, in particular downstream of wastewater treatment plants, where there's a lot of this more emerging contaminants as well as pathogens that treatment plants can't deal with, actually then accumulated in streambed environments. And one thing we focus on a lot is how variability in flow, low flow conditions versus high flow conditions, are really conditioning how much accumulation you see in this streambed environments, or how much remobilization of particles or pathogens that have been accumulated there potentially a long time ago you are seeing. So that threshold between deposition and then reactivation. There's another reason why we see rivers storing micro nanoplastic for a long time, why I would call them a temporary storage zone. And that is that the majority of our rivers are regulated. That's also why that initial predictions that 10 or 20 rivers are the main contributors of plastic to the ocean, I think, is evidently wrong. The majority of that rivers, you see them here on the right-hand side, these are the 20 supposed rivers as the main contributors. Apart from two, the Congo and the Amazon, they are heavily regulated. That means they have dams and reservoirs. Upstream of a dam, flow velocity drops down to virtually zero, and with that, we see deposition of particles, not just micro nanoplastics, generally sediment. There's some coming through, of course, but one thing we see is that upstream of dams, we see a huge amount of accumulation of micro nanoplastics in the sediment. We see that much more in large rivers than these are arbitrary classification we used in our model here. We said small, intermediate, and large rivers. Intermediate ones are up to 1,000 square kilometer catchment. And you see the free-flowing parts of rivers globally, which are the blue zones, are much larger in this intermediate basin sizes than they are in large or in small rivers. Yeah, there's 2 to 3 times the capacity to carry. Whereas in many large rivers, those really free-flowing ones are in areas where we have much less sources that can get activated. So I really don't think that large rivers are over proportionally big contributors to micro nanoplastics to the ocean. Again, that's all modeling work. If that doesn't get validated, we don't know how true or false it is. I just want to highlight one program that we've just concluded here, but the global sampling is continuing, which was 100 plastic rivers, where we rolled out a program and invite everyone to collaborate with us on the continuation of that. We rolled out a standardized protocol for sampling and then for analysis to actually generate some benchmark data that are comparable globally to falsify this type of models. I show you some results of individual sizes here that are helping to validate or prove our models wrong. One is actually very close to our doorstep here. It's the River Thames, supposedly the most polluted river in Britain. You see Birmingham is just on the south here. That's Birmingham. And we had a long time ago a master's student actually doing a study there where he wanted to look into how microplastic concentrations in the sediment are increasing with increasing population downstream, because that is still the main assumption of other global models. So he sampled downstream that river and some of the tributaries and saw, yes, initially as you go downstream from the left to the right here, there's an increase in concentration, then it drops. Again, there's an increase in concentration, then it drops. You will not be surprised when I tell you the reason that it drops is because there are some small reservoirs, you see them actually in here, they're Victorian, they are relatively old, that reduce the flow again, so we see accumulation upstream of that reservoirs, but downstream there are less particles in the surface water, so less can actually be deposited in the sediments. Yeah, so it's something that it's a relatively large, small scale. So we are looking into larger scales as well. I have a secondary affiliation with the University of Lyon in France, and Lyon lies on the River Rhone, which is the largest river in France. It comes from Switzerland, and between Switzerland and Lyon is what's called the Plastic Valley. That's one of the major hotspots of plastic production in Europe. But the River Rhone is also heavily regulated. So if you look upstream to downstream, a section of the tributaries of the Rhone here, the River Arno, you see a lot of really cascades of dams that are shown with this black triangles, and zoomed in there then some areas. There's a lot of small dams in there as well. On the right-hand side, you can see density of plastic production by different plastic producing companies. What we see there as well is a very similar picture at a much larger scale. So you see microplastic concentrations in sediment rising, and it drops, in particular where we have higher densities of dams before it starts increasing again. So as a hydrologist, I really have to say it is the flow, it is the transport that rules what we find in surface waters and in sediments. And we can't ignore that if we want to predict exposures. I come back to that just in a few minutes, because unfortunately, a lot of our regulatory frameworks globally do. And I think we need to be better advocates for this, making sure this type of knowledge is used in regulation as well. I go one step up. I used the Ganga as an example before. We did a large survey with many Indian partners and a couple of international partners along the Ganga in 2019, just post-monsoon. And what we found there was that micro nanoplastic concentrations along the river, you see that here again in sediment, we find real hotspots upstream already. This is close to Haridwar, one of the holy sites of the Ganga, just where it emerges from the Himalayas. Then the concentrations drop again. Then they increase somewhere else. We don't see this increase downstream as many models are predicting. Yeah, and the surface waters, that as you see here, we see hotspots. Interestingly, again, they don't coincide with what we see in the sediments. Yeah, which to a degree makes sense, because it's correlated with the deposition and resuspension behavior that we are seeing. If we compare that to other contaminants, we see that there's some correlation to a degree with some of the indicators of wastewater inputs. But otherwise, these hotspots are pretty distinct, and they don't show that there's a convergence of fluxes downstream, also not if we calculate the loads. The main reasons for that, similarly, the amount of obstructions of flow upstream of barrages, a reduction of flow velocity upstream of barrages, and water that is obstructed, used in agriculture before some of the water flows back into the river, and impacts of big tributaries. So that interference with flow is one that can have significant impact on the distribution of micro nanoplastic. I'll show you the last field example for today here, where we learned a lot about that at a slightly smaller system again. So I try to weave in a bit of physical evidence here that we use to falsify that global model that we are using as well. What you see here is micro nanoplastic concentrations in sediment and surface water at Boulder Creek and South Boulder Creek, small rivers compared to the Ganga. Boulder, 250,000 inhabitants, just at the foothills of the Rocky Mountains in Colorado. If you look into the concentration profiles, they don't look that interesting, actually. You can't make much out of that. What looks more interesting is if you look into what determines that concentrations, in particular the fluxes, the loads of micro nanoplastic, as we are looking downstream. What we see when we go downstream, Boulder Creek and South Boulder Creek, is a lot of these features. Some of them are quite old. They're obstruction features where water is taken out of the main river, going into agricultural irrigation systems. They are sometimes transported up to 200 kilometers away from the river, actually into different river basins. If you calculate the fluxes that are taken with the obstructed water, you see that for Boulder Creek at the top and for South Boulder Creek at the bottom, these are not the concentrations, but the total amount of particles per second of flow. And you see there's expectedly an increase at one point, but then a lot of that, which is shown in this shaded areas here, that's obstructed. That goes out of the catchment. For South Boulder Creek, a lot in the beginning, and then again, a lot further downstream. This is going into a different catchment. This is having an impact there. This is continued to be transported there, but not in the catchment where global models, including ours, would so far predict that. And I think given how much irrigation obstructions we have, in particular on large rivers globally, this is something we seriously need to take into account if we want to predict exposures. Yeah, I'm coming to the end here. If we want to predict and actually mitigate impacts of micro and nanoplastics and many other contaminants, we need to, and it's fantastic to speak in particular in this series for eco-environment and health. The only way to do that is to tackle this global challenge with One Health solutions, where I think I highlighted to you, there are environmental risks, there are human health risks. We do a lot of ecotoxicological research, increasing human health research as well. Haven't talked much about that today at all. But they are, of course, interconnected. Our own exposure is not only direct through the water that we are taking, but also through what we are taking up the food web. So we have to combine this direct, indirect exposure assessments, of course, but also the functioning of ecosystems that is potentially affected by micro nanoplastic has an impact on our well-being. So One Health solutions are the only way forward. I want to highlight for that when we talk about, I really like this concept of the environmental exposome. So basically everything that an environment is exposed to. I talked mainly about chemical exposure today. I give you one very brief example for pathogen transport. So there's more of this biological exposure as well can have an impact. But of course, the physical exposure, so the change to whether it is flow conditions, that is temperature, for instance, has a significant impact on both biological and chemical exposure as well, and we need to take this into account. I gave you a couple of examples of what we know, and I hope I highlighted enough what we don't know yet as well. However, one of my frustrations is that when it comes to regulatory tools that are used, and I give you some here that we are using in Europe, where we have the registration, evaluation, authorization, and restriction of chemicals and compliance framework of the European Chemical Agency and so on. A lot of the tools that are used there are extremely simplified tools. And of course, we need simple and easily applicable tools, but they don't take environmental transport processes really into account. All the predictions of exposure, they are based purely on the material properties that of contaminants that we are looking into, and some oversimplified representations of the fate processes that have nothing, like all these flow processes that I've shown you, and you could show similar examples for atmospheric exposure. They are not considered. I'll give you an example here on the right, how oversimplified, for instance, soils and the subsurface are represented there. That means if we can't access the risks adequately, there's no, the exposure adequately, it's absolutely clear that our risk assessment will be wrong. And I think we need to be advocates as scientists of getting more of this mechanistic process understanding into this operational models. Not just our scientific models need to be improved, but also this operational tools. Talking about the subsurface, we do a lot of research, for instance, on micro nanoplastic transport in the subsurface, as many of our groundwaters get increasingly exposed. And I've shown that, for instance, through transport, through porous media, like in soils and groundwater, where you can see that we created even more legacy there than we did in stream sediments, a legacy that's going to last decades and centuries, definitely generations. Let's try to go beyond that. So to summarize here, I hope I could show you that plastic contributes to disease burden, in particular of non-communicable diseases globally. However, in order to assess individual risks, we need to understand exposure controls and what mechanistic drivers control this exposure. I give you some examples of the hydrological drivers. We work a lot more on atmospheric pollution as well, with micro nanoplastic. That would be different examples. Yeah, but if we want to understand uptake risks, we need to understand this exposure. And as environmental scientists, we have a lot to contribute there. We need a louder voice. We need to be better advocates. Yeah. One thing I hope I've also convinced you of is that it's the hydrology, but also how we manage water that has significant impact on micro nanoplastic exposures and how they are transported, much more than only the sources, which is what previous models have assumed. That really we don't see a convergence of fluxes downstream, but very patchy distributions with real hotspots along, for instance, river networks, as well as rivers being long-term, river networks being long-term storage areas as compared to oceans, which received only very few of the emitted plastic waste so far. If we want to quantify these exposures to micro nanoplastic, we need to understand the mechanisms how rivers control activation of plastics as well as co-contaminants and their sources, and how they connect them, to receptor systems. There's of course a complexity added to that. That water is acting as a transport agent for not only for plastic but also other contaminants that are interacting in the environment. But we need to understand this if we want to prevent environmental pollution-induced shocks. And it really requires community efforts to actually understand this One Health risks better. I'm highlighting here, I'm going to finish with one or two slides on that, a couple of initiatives on that. The Helping Initiative of the International Association of Hydrological Sciences is one of them. We host a One Health workshop as a IHS international meeting in Rocky, India in 3 weeks. You're all very invited to participate in there. I think we need, as scientists, to become better advocates for and provide more policy advice there as well. I give you two examples here on the left. They've been trying to do that with local government in the UK through a policy commission and now an all-party parliamentary group that we initiated. But we work a lot with NGOs as well. Some of you may have seen we had the UN INC negotiations for a plastic treaty in Geneva, the 5.2 round that didn't succeed. It didn't come to a conclusion in August, but this is a story that's going to continue. And we worked with WWF, for instance, to create an output. We could have probably published 3 papers in that time. I think it is a more important output than 3 papers. Putting together this Plastic Health and One Planet. It's a 60-page document that was designed with WWF and handed over to all the negotiation teams, the national negotiation teams, to inform their position on not only what are the environmental health risks, which were more understood already, but what are the human health risks, why are they fragmented, and how can we improve that evidence? I want to finish here with inviting you all to 2 things. For one, we are going to host, and together with people involved in the journal Eco-Environment&Health, a conference in July 2026, where we are trying to bring together the communities that are still not talking, unfortunately, much with each other, focusing on the environmental, fate, transport, and health risks, and those focusing on the human health risks of micro and nanoplastics. We try to bring that together in a One Health focused conference. We call them MNP for Micro Nanoplastic 26. I really would like to invite you all to participate in that. The website of the conference, we've just announced it, is the link to that is given on the top. Get in contact with us. The abstract submission is opening in the next couple of days, registration as well. I would really love to welcome you to that in Birmingham. And to finish with one big issue that we are facing when it comes to assessing micro and nanoplastic is that we have no standardized protocols for quantifying, identifying, characterizing micro nanoplastic, whether it's in environmental matrices or in human tissue, organs, body fluids, and so on. For that reason, now for several years, we have been running very successfully a workshop where we try to help the scientific community globally on environmental micro nanoplastic identification and characterization. We do that in Birmingham. We have one picture up here where we are showing how micro nanoplastic are sampled from water and sediments. We did do a lot of research on that, highlighting that even the way we sample before we analyze anything can create almost 2 order of magnitude differences on what we are detecting. This is an event that we are hosting every year. The next one is going to be the first week of February in 2006 in Birmingham. It's really an event for the community. We keep the numbers relatively small because it's a very hand-on experience. So we try to not have more than 15, maximum 20 participants in that, so that people really can use all the instrumentation and laboratory equipment together with many of the experts that we have over here and invite for that. And again, I invite people who are interested in that to contact us. There's a link already on the top as well where you can register for that. And with that, I would like to thank our fantastic team in Birmingham and many of our collaborators, our funders, and a lot of our collaborators globally as well, because a lot of the research that I've demonstrated here wouldn't have been able to be conducted without many of our fantastic collaborators across many Asian countries, South America, parts of North America as well, and some parts of Africa, Europe, of course. So thank you very much for your attention. And a really massive shout out to many of the early career researchers in particular that have helped us with this research. Thank you very much. Looking forward to some questions.
Thank you, Professor Cross. I see there is already a question in the chatting box. Thank you, Professor Cross. Give us many indications of linking transport mechanisms of microplastics to explorer risks and outcomes. And also the conference information in Birmingham. Let's look at the first question. Is there any relevant standard for the concentration of micro and nanoplastics in water environment in the world at present?
It's a really good question, and I have an answer only that doesn't satisfy me or anyone as well, which is no, unfortunately not yet. So there are unfortunately no standardized reference methods that are used. There are many different methods. We use methods from fluorescent microscopy to micro FTIR, micro Raman spectroscopy, pyrolysis GCMS, and others in our laboratory. They all give you different insights into the problem with different resolutions, very importantly, different sample throughput numbers and different size cutoffs, like how small the particles can be that we can analyze with that. However, you can apply these methods in very different ways. But even when it comes to how much should be sampled, how much water should be sampled, how should it be sampled, what auxiliary information should be actually collected with it, there are no standardized protocols that have been globally accepted. We have rolled out with our 100 Plastic River program one method where we try to standardize this so that we can get comparable data, because I'm more than happy to distribute some of the publications that we had where we have been comparing how important is the application of different methods for the results that we are seeing. And we've seen, unfortunately, what has been published globally with different methods. I'm not saying one method is worse or better than another, but they're so different that it's almost impossible to compare that results. And if we don't end up with standardized methods for sampling, for extraction of micro nanoplastics, so the ways how we digest, for instance, how we remove the particles from the substrate before we analyze them. And then, of course, for the analysis, before we don't have standardized pipelines for that are agreed, it's really hard to compare. There's the intention to do that. There are pushes. The European Chemical Agency, for instance, is pushing for that. I know our partners in China are pushing for that. I hope we are getting there. But I also don't think there will be one method that fits all. Sometimes there's worrying, pushing for we should have one standardized method. I don't think that is the correct way forward, because there are very different demands on if we analyze micro nanoplastic particles in bloods, which will be a very small particle size, or if we analyze them in the air as compared to if we analyze them in soils where we have very different organic matter content and very different particle sizes and co-contaminants as well. So we will probably need different methods for different compounds. And we will need good suites of standard materials to actually use in our QA, QC procedures for methods that are applied in order to show how well are we operating, even when we have standardized procedures, how well are we operating that protocols in individual labs. So similar to standards that we're using for when we're analyzing nitrates, for instance, in a lab. Sorry, that was a lengthy answer, but it's really a complex challenge. Really good question.
Yeah, we have a standard in the near future. And the other question is for the health risks of microplastics, do you think whether there are some environmental factors should be considered firstly? Yeah.
Absolutely. And for multiple reasons. So let's start maybe with one. One thing that global research has already shown is that the exposure to the same type of plastic carries a different uptake risk if there's a comorbidity. So I mentioned right in the beginning that exposure to some types of micro nanoplastic can cause inflammation. However, there's also a mechanism in the other direction. If you have an inflamed tissue, and that has, for instance, been done for gastrointestinal tract tissues, where a lot of people suffer from irritable bowel syndrome, IBS, for instance. It has been evidence that patients with IBS, with an inflamed, irritated gut, take up more and easier micro nanoplastic and their additives than if that comorbidity doesn't exist. So yes, the condition of the patient have definitely an impact. The environmental conditions have definitely an impact. Uh, if I if I use maybe a different example, of course, you can imagine diet has a significant impact. If I take up the same amount of micro nanoplastic, but with different diets, and whether it's a vegetarian to someone who's an omnivore, meat eater, someone who has been starving potentially, a lot of exposure in low and middle income countries, to someone who is obese, right? There will be very different uptake risks. And the same for inhalation, of course. And whether that is done at a certain humidity, temperature, etc., when it comes to inhalation, has an impact on the particle properties, but also on what eco-corona as the particles we are exposed to are. Usually they're not pristine unless you're a factory worker that works where the particles are still very young, but often they have been transported for a long time in the environment. That means they've interacted, they have environmentally aged. That means there's some coverage of a biofilm or eco-corona on them that has an impact on how easily, but how they are transported, but also how easily they're taken up and what impact they can cause. So yeah, these environmental factors have a significant impact. They interact. That's why I stressed at the end. We really have a very multidimensional challenge here. It's not just that there are cocktails of different contaminants we are exposed to, but also many other stressors that are increasing due to climate change and so on. I try to keep my answers short because I see there's some more questions coming through.
Yeah, yeah. The next one is which is the more critical factor affecting plastic settlement, the watershed size or the flow velocity? Which one
Was
do
that
you think?
the shear size or flow velocity?
Yeah, the watershed size to
Yeah,
affect the plastic
they
settle.
they they are not independent of each other, of course, right? So like that, they interact. And one thing we are seeing is that the impact both of them are having varies significantly from multiple conditions. One is the viscosity of the water because that is temperature dependent. But more importantly, it's the particles themselves. A lot of research traditionally has been done with spheres, just because they're easily accessible. However, many micro nanoplastic particles that we find in the environment are not spheres. They are very irregularly formed fragments or fibers. We hardly understand how fibers are moving at all. We started some research on that. Uh, and it has a massive impact on how what the plasticity or elasticity of that particles is, fibers in particular, but also films. So for which we find very often in the environment, the bed forms, if we stick to rivers, and the roughness of that bed forms, often given by the sediment structure, but also what's growing on that bed forms, has a significant impact as well as what grows within that porous matrices. So whether there's significant benthic biofilm growth, for instance, in them. So there's no clear answer that one is more important than the other. One thing we see is that a real driving factor are the particle properties, uh, but the particle density has an impact, of course, but that's a shape which is, of course, very complex. Uh, is a property that probably has been understudied so far as well, the shape of the particle.
Okay, yeah. The other question is, did the water samples in your study analyze other emerging contaminants such as PPCP, antibiotics? How to determine the priority control pollutants?
Yeah, that's often very context dependent. So we did run studies where we tried to have very high throughputs of samples, and for that reason looked into less parameters. So some studies where we try to have hundreds of samples being analyzed, we can't look, or thousands in fact, we can't look with the same not rigor, it's the same rigor, but with the same complexity of co-contaminants as we do in other studies. This 100 plastic river program, for instance, we only looked into the main polymers. We didn't analyze additives, for instance. In other studies, we analyze the additives that can be brominated flame retardants we are concerned about, for instance, because they are cancerogenic, and we have collaborators here in Birmingham that looked into what is the load of brominated flame retardants in some of our globally sampled microplastic concentrations. In other samples, we looked indeed into the amount of bisphenols, what is in there, but also what is leaching out under what conditions. Phthalates is one thing we are very interested in. We started to look more into pathogens as well, in particular when we look into micro nanoplastic that are still coming out of wastewater treatment plants. Most wastewater treatment plants are pretty efficient captors of micro nanoplastic. They can keep more than 95% of micro nanoplastic, but then at least in Europe, unfortunately, still a lot of that sewage sludge is then used. So where we accumulate the problem that's used, it's brought out in agriculture and used as a fertilizer. So we redisperse it, which sounds insane, I know. So we capture a problem and then we bring it back out into the world. And what concerns us there in particular is then that it's not only micro nanoplastic, but many other pathogens. Enteric viruses is one we are particularly interested in, for instance. I think you mentioned antimicrobial resistance, right? And antimicrobial resistant genes that are at much higher risks than to be co-transported with micro nanoplastics. So yes, in some samples, in some studies that we have been running, we are looking into that, but our level of detail we look into is really study dependent. We don't always analyze the same co-contaminants in every study.
Okay, I followed his question. I have a question because I take some related courses of microplastics and do some research on the interaction between environmental microorganisms and microplastic exposure myself. My students always ask me in class, and I often ask myself in return, if the toxicity of nanoparticles or microplastics is not so toxic as compared to many other pollutants, then do we still need to spend so much energy to study or investigate this kind of pollutant? How do you deal with this kind of problem?
I think it's a very justified question. And indeed, if we see that for certain types of plastics or also some of the additives, ecotoxicity is low, then that's great. That's something we have to worry about less. We have to worry about those where it is not, right? And I think there's some questioning. I'm not an ecotoxicologist myself. I've worked with ecotoxicologists, and many ecotoxicological studies are done with non-environmentally realistic concentrations, with higher concentrations than we think we find in the environment. That's why I think it's very important that more recently, exposure studies, ecotoxicological studies, but also studies with organ-on-chip models, cell cultures, are done more with what we think are environmentally realistic exposures. I understand why traditionally ecotoxicologists work with higher exposures, because if you can show that even a high exposure doesn't have an impact, great, we don't have to worry, right? If it shows an impact though, then we have to see what is impact of an environmentally realistic exposure. I think the challenge we see there, so two quick things, is I don't think we know what environmentally realistic exposures are quite often yet because they vary a lot in space and time. And as we are only getting better handle on technologies to look into the nanoscale, we see that the particle numbers at that scale are significantly higher than at the microscale, which is not that unsurprising actually, but for that reason, I don't think we know what realistic exposures are yet. We did exposure experiments with several model systems from chironomids to tubifex worms. Mainly we looked into with many collaborators, bioturbating species, and usually used environmental realistic exposures only. And we saw significant sublethal effects for some of the polymers, not for all of them, but that's exactly the important thing, finding out which are those that we have to worry about, which are those that we don't have to worry about. And I think quite often it's not down to the polymer, but to the additives that are used there as well. We found, for instance, that medical grade polymers as compared to those that are controlled for food standards or not controlled, even if it's the same polymer but have different additive composition, have very different impact on the functioning of microbial biofilms, for instance. So it's often the additives, not the polymers, that cause the effect. Sorry, again, too long answer.
I think maybe there will be some interactions we didn't mention in the environment. They will influence each other's ecotoxicity.
Absolutely. Yes, absolutely. And a lot of those interactions are still unexplored. So one thing we are seeing in multi-contaminant exposure study is that thresholds that we regulate, in particular for the contaminants that we understand better, are usually related to individual contaminants. How often in the environment we are exposed to complex cocktails of contaminants, and often the thresholds of effect can be much lower. We did a lot of controlled studies. We run a controlled river lab where we have more than 100 rivers that we simulate over here. The same for groundwaters or soils or wetlands. And that allows us to look into combined effects. And we see, for instance, that engineered nanoparticles that we work with as well have different effects on microbial biofilms at different stream temperatures. That of course interact or based on the reception of different intensity of UV radiation or co-contaminant with other pollutants. So for these threshold concepts that we use with regulators for individual contaminants are a little bit risky, I think, because quite often we see particular sublethal effects already at lower concentrations if there are interactions with other contaminants, which
Yeah,
there usually are in the environment.
yeah. We never know.
Yeah.
Well, I hope we could know that in the near future.
I think
Well, yeah,
and I don't want to just blatantly shout out for new data science tools like the more advanced AI or deep machine learning methods, but I think there's huge potential to apply these also for when it comes to looking into combined effect models, for instance.
wow, yeah. That will be a research direction for both of us.
And the generations after us, yes, our students. Yeah.
Yeah, thank you so much, Professor Cross.
Thank you very
Is
much also for the really interesting
yeah,
questions, quite stimulating.
is there any more questions? 徐老师，那我们就结束了哈。谢谢各位，Thank you everyone. Thank you, Professor Cross. Hope we
Thank
can
you for a very kind
see you next time.
invitation. Thank you.
Okay,
Thank you
thank
very
you.
much.
Bye
Have a good
bye.
day. Good afternoon over in China. Bye.
Yeah, yeah. Bye bye.